So now welcome back to the next session on time-dependent perturbation theory. So we were discussing the atom field interaction. Okay, so this is one of the last topic of the atom field interaction. So we discuss about the induced emission and absorption. Absorption. So particularly, we are going to discuss about the transition probability. Okay, so we have to recall two things. The first of all, in quantum theory, what is the expression for the atom field interaction Hamiltonian? So we have discussed in the last lecture, that is the interaction, the atom field interaction Hamiltonian, which is basically E by mc a dot p. This can be written as E by mc square root of 2 pi h cross c square divided by capital V omega k, then sum over lambda, annihilation operator, then e raised to I k dot r e lambda dot p e raised to minus I omega t plus a lambda dagger e raised to minus I k dot r e lambda dot p e raised to plus I omega t. Okay, so this can be written in simple terms as sum over lambda v lambda e raised to minus I omega lambda t plus v lambda dagger e raised to plus I omega lambda t. Okay, so this capital V of t. So this we have discussed in detail in the last lecture. Okay, so this thing we have to remember. Now the next thing is we already discussed the transition rate for the harmonic perturbation. So this look like symbol harmonic perturbation. Now, what about your the transition rate for the harmonic perturbation? So, suppose if your the interaction potential is small v e raised to I just look at it e raised to minus I omega t plus v dagger e raised to plus I omega t. Then there are two possibility. Okay, so this e raised to minus I omega t actually refers for the absorption of energy. This basically represent the absorption term, and this term represent the emission. Okay, so the energy would be absorbed in this process. This Hamilton, this interaction potential represent the absorption of energy, and this term represent the emission of energy. Okay, and what about the transition rate? It is gamma. The system goes from I to F. The absorption of energy is absorption, also referred as excitation of state, 2 pi by h cross the mod square of inner product, the final state V, initial state, square the Dirac delta function EF minus EI minus h cross omega. Okay, so that refers for the absorption or excitation. Okay, that is the system goes from some energy level to a higher energy level by absorbing some energy from surroundings. Okay, from perturbation. And what about de-excitation? So de-excitation, also referred as emission. So energy would be emitted I to F. What would be that expression? That would become 2 pi by h cross the mod square of the inner product psi f, and there comes v dagger psi I mod square, the drag delta function ef minus ei plus h cross omega. Okay, now if you know these two things, that is the expression for the interaction potential for atom field interaction in quantum theory, and as well as the transition rate for harmonic perturbation, so we can easily find out the transition rate for the atom field interaction in quantum mechanics, that is when you treat the field as a quantum variable. Okay, so that those transition rate we can find out. Transition rates. Okay, so now we are going for some approximations. Okay, so what one approximation or one assumptions that we are making is the field contains only one mode. Okay, so assume the electromagnetic field has only one mode. So if it has only one mode, then there is no need to sum over all lambda. Okay, and what about your this interaction potential? So this interaction potential, the term there are two terms v and v dagger. So how can I write my v here? So this v can be written as e by mc square root of 2 pi h cross c square times by v omega, then e raised to I k dot r e dot p annihilation operator a, and v dagger, just all this term, this a become a dagger. Okay, so this would be your v, and what about your the interaction potential? The interaction potential capital V of t, that is simply become v times e raised to minus I omega t plus v dagger e raised to plus I omega t. Okay, so what I have done is I have removed the sum over lambda here, because I am assumed the electromagnetic wave contains only single mode. Okay. Now the another thing is earlier while we are writing the transition probabilities, okay, the transition rates, I have referred here psi I and psi f, but now here there are two systems. One is atom and field. Okay, so therefore the psi I is the tensor product of two states. One is the psi I of atom and Ni, where Ni represent the state of the field. And what about psi f? Psi f is the psi f, the final state of atom times Nf. Okay, so I'll be using this expression in the next pages. Okay, so then what about the transition probability or transition rate? Okay, so we can first go for the transition rate for this refer for absorption. Okay, so the transition rate for absorption or excitation. So gamma absorption from I to F is 2 pi by h cross the mod square of psi f atom comma nf. Then the V takes the form E by mc square root of 2 pi h cross c square v omega e raised to I k dot r e dot p annihilation operator, then psi I atom comma ni mod square, then Dirac delta function EF minus EI minus H cross omega. So this means that this transition, this absorption is possible only if EF equals EI plus H cross omega. That is the final state of the atom would be EI plus H cross omega, where EI is the ground state. So that means in this process, uh, the uh, the atom has to absorb a photon H cross omega in order to reach the final state. So obviously, for in order to do that, the number of photon has to be decreased by one, so that we can see it here. Okay, now if you look at there is an annihilation operator A. This annihilation operator A acts only with Ni, so we can divide this into two terms. Okay, so better I will copy this term to the next page. Okay, so this can be written as 2 pi by H cross. We can take some the constants outside, so E square by M square C square 2 pi H cross C square divided by capital V omega, and all other terms would be inside. Okay, so there would be some NF annihilation A Ni mod square, then psi F atom e raised to I k dot r e dot p psi I atom mod square, then Dirac delta function EF minus EI minus H cross omega. Now what about this term? Okay, so this term would become NF A acting on Ni is square root of Ni, then Ni minus 1, because A acting on Ni reduces the quantum number by 1. So this become like this. Okay, so square root of Ni square can be taken outside, that become Ni, and NF Ni minus 1, that become a Dirac delta function NF comma Ni minus 1. Okay, so therefore I can write, okay, so we can have some simplification here. So this become 4 pi square, I think H cross would cancel, and C square would also cancel. So 4 pi square E square divided by V omega M square. Then this become Ni can be taken outside, and then so if you take Ni outside, then what would be the remaining? That the remaining would be the inner product NF Ni minus 1. Okay, now these are the orthogonal operator. Okay, sorry, orthogonal vectors, orthonormal vectors. So their inner product would be a Dirac delta function. Okay, oh sorry, not Dirac delta function, it will be a Kronecker delta function. So this will become Kronecker delta NF comma Ni minus 1. Okay, I think this is familiar to you. The inner product Mn, I can write a Kronecker delta M comma N. So that means it would be 0 when M not equal to N, and it would be 1 when M equal to N. So that is its meaning. Okay, so since the eigen vectors corresponding to an Hermitian operator are orthogonal, so it is possible to write. So since this Ni and the Ni and Nf are just the eigenvectors of the number operator A dagger A, which is a Hermitian operator. So therefore, all its the eigenvectors, that is the ket n's, would be orthogonal. and you can normalize it as well. So I can define an orthonormal eigenvectors for the number of operators. So that result I have used here. So this inner product can be written as the canonical delta nf comma ni minus 1. Then I can just write down what are the remaining quantities here. So this become the mod square of inner product psi f atom e raised to I k dot r e dot p psi I atom mod square the Dirac delta function ef minus ei minus h cross omega. Okay, so 1 second, so I will copy it once again. Okay, now we have got the required things to us. So what is this? So this basically the transition probability corresponding to the absorption of energy, the transition rate corresponding to absorption from I to F. So here you got a canonical delta function here. So that means this transition is possible. Okay, so that means the absorption of energy is possible. There are two conditions. The first condition is this EF minus EI minus H cross omega must be 0. That means EF must be equal to ei plus h cross omega, and the other one is this nf and ni minus 1 must be equal. That is nf must be equal to ni minus 1. That is the number of photons must reduce by 1. Okay, so when the atom going from a lower state ei to higher state ef, then ef must be equal to ei plus h cross omega. Then the number of photons ni a number of photons nf, the number of photons must reduce by 1. So in this process, 1 photon of energy h cross omega will be absorbed. So this kind of absorption is called the induced absorption. Okay, now remember this absorption is not possible if initial number of a photon is 0. Okay, so the absorption is not possible if ni equal to 0. So that means initially we required some number of photons. Okay, so we are the ni must be always non-zero. That means there should be the presence of some photons in order for the absorption of energy of the atom in order to go to the excited state. Okay, and there is no the great thing over here, because this is already known to us. That is, whenever a system has to go to the higher energy, then we have to supply some external energy. Okay, in some form. Okay, in electrical form or in the form of light, photon, etc. Now, what about emission? So similarly, we can do it for emission. That is gamma I to F emission. So what would be that expression? So that would be 2 pi by h cross the inner product psi f. Okay, over here there are atom nf v dagger psi I atom ni mod square, and the Dirac delta function ef minus ei plus h cross omega. Okay, now the same thing we can do it here. Okay, I already know the expression for v dagger. Just substitute it and do the all the simplification that we have already done for the absorption. Okay, so the emission process, or it's also called de-excitation process. So if you do all the simplification, I can show that this becomes 4 pi square e square divided by m square omega v, then n plus 1, the chronicle delta. Okay, what we have got, the earlier chronicle delta, we have got chronicle delta nf comma ni minus 1. So here it become uh, nf comma ni plus 1, because we have to add dagger with ni, so there you get ni plus 1. Okay, so direct delta nf comma ni plus 1, then the mod square of psi of atom e raised to minus I k dot r e dot p psi I atom mod square, then the chronicle sorry Dirac delta ef minus ei. Okay, better I will write in the next line ef minus ei plus h cross omega. Okay, so in order to get the non-zero, the transition rate, what should be, this must be non-zero and this expression must also be non-zero. Okay, so there are other conditions as well that we'll discuss in the next session, that is this term should also be non-zero. Okay, so that we can condense a dipole approximation, so we have to use the dipole approximation in order to find that condition, so that we'll do in the next session, next lecture. Okay, so anyhow, apart from that, there must be these two conditions. Okay, so the first of all, in order to get non-zero value for this chronicle delta function. Okay, so in order to get non-zero emission, the first one is this nf must be equal to ni plus 1, that is the number of photon in the higher, in the final state must be number of photons in initial state plus 1, and what is the other thing is ef, the final energy must be equal to ei minus h cross omega. So that means if you have two energy levels for atom, the initial energy and final energy, so the atom goes from atom, the energy lowers by h cross omega. Okay, so the final energy is equal to ei minus h cross omega, and the number of photons initially is ni, and what should be the final number of photon, that must be equal to ni plus 1. So that means some photon will be liberated in this process. Okay, so that is why this process is referred as emission or a de-excitation. Okay, so while de-exciting, when the atom goes from to the lower state, one photon will be emitted. Good. Okay, now this thing also is very known to us, that is whenever the atom de-excites, there would be emission. Okay, now there are two possibility. One is the emission is possible when ni is non-zero. Okay, so emission when ni non-zero. So initially, if the number of photon is non-zero, then there can be emission. So such emission is called stimulated emission. Okay, so with the influence of the other photons, the atom get emitted. So such kind of emission is called stimulated emission. Now the emission can happen even if ni becomes zero. Okay, because nf only ni plus 1. Okay, so if ni is 0, then nf can become 1. Okay, so only thing is the nf must be equal to ni plus 1. So if ni is 0, then nf can be 1. So that means this kind of emission can be possible even if no photon presence, even in the absence of a photon. So emission can happen even if ni is 0. So if ni is 0, then such kind of emissions are called spontaneous emission. Okay, so earlier when you are discussing the classical theory or semi-classical theory of the atom field interaction, we could not able to account the spontaneous emission. So there, in order to have the emission or de-excitation, the field must be present always. But here you can see that in even in the absence of a photon, the atom can emit a photon. Okay, so even if the initial number of photon is zero, there can be emission. So such emission will gives the theory of spontaneous emission. Okay, so we are not going to discuss much about the spontaneous emission in our discussion. So if you want, you can read it, the quantum theory of the spontaneous emission. Okay, so anyhow, this is what we want to discuss in our this session. Okay, so this session basically discuss about the induced emission and induced absorption. The induced emission and induced absorption is basically the absorption emission in the presence of photon. That is when the initial number of photon is non-zero. Okay, and the other emission is called spontaneous emission. There cannot be spontaneous absorption because there must be the external photon in order to excite the atom. Okay, so there cannot be spontaneous absorption, but there can be spontaneous emission. That is, even in the absence of photon, the atom can emit a photon, or the atom can go to the lower level. Okay, so with this remark, we are stopping our discussion of today's topic. And next, we'll discuss the dipole approximation. And dipole approximation basically comes from this term. Okay, so recall this term. So this term, in order to get non-zero, the transition rate, this inner product must be non-zero. Okay, so that is a third condition. So two conditions we have discussed. Now the third condition is this inner product must be non-zero in order to get the excitation or de-excitation transition rate. But the condition for this particular inner product become non-zero is not very straightforward. We have to use some approximation to do that, and such approximation, the approximation that we are going to use is called dipole approximation. Okay, so that would be our the last session of this time dependent perturbation theory, the transition rate with the dipole approximation. Okay, so thanks for watching. We'll see you in the next class.